In this video, we look at one of the simplest and most common forms of chemical analysis carried out in chemical laboratories. That is titrations. Despite the advent of sophisticated spectroscopic forms of analyses, the simple titration is still the preferred method of chemical analysis in many cases, including the determination of acidity or basicity of a solution. In a titration, a standard solution is used to determine the unknown concentration of a solute in a second solution. And, just to recall, a standard solution is a solution where we accurately know the concentration of the solute. Titrations involve the gradual addition of the standard solution to the unknown solution until all of the reactant in the unknown solution has been completely reacted. It's important to note that the solute reactants of both solutions need to react in a known and predictable way. And when it comes to acid-base titrations, for example, we are already very familiar with how these two types of substances react, since we know that an acid plus a base gives us a salt plus water. And we know that if we were given the identity of an acid and we know the identity of a base, we are now able to write a balanced chemical equation for that acid-base reaction. So let's say, for argument's sake, we wanted to determine the concentration of phosphoric acid in a solution. And here we have a pictorial representation of a phosphoric acid solution with an unknown concentration sitting in a beaker. Now remember, the purpose of a titration is to determine the unknown concentration of a solute in a solution, in this case phosphoric acid. The first thing we do in a titration is to start by accurately preparing a known volume of the acid sample. So, for example, we accurately dispense 20.0 milliliters of the phosphoric acid solution into the beaker. What we then do is gradually add a base to the solution until all of the acid has been neutralized according to the general acid-base neutralization reaction scheme shown above. So let's just say, for argument's sake, that the base we used was barium hydroxide. We would then add the barium hydroxide solution to the phosphoric acid solution until the acid was neutralized. Now it's important to note here that the solution that we add is a standard solution. We know the concentration of it accurately, and let's say, again, for argument's sake, that the concentration of the barium hydroxide solution is 0.100 molar or 0.100 moles per litre. The next thing we do is record the volume of the base we need to add until we get to the neutralization point. In acid-base titrations, the neutralization point, or the equivalent point, is determined by the use of an acid-base indicator, where the solution will undergo a noticeable colour change at the equivalence point. So here's the scenario that we set up experimentally. Down the bottom, we have exactly 20.0 milliliters of an unknown concentration of phosphoric acid, with the acid-base indicator added. In the burette above, we have our standard solution of barium hydroxide, a 0.100 molar solution, and the burette is used to deliver an accurately known volume of the solution. To start the titration, we gradually add the barium hydroxide solution until we see a colour change, and then we turn the burette off and we record the volume. So let's say, for argument's sake, it took 26.4 milliliters of the standard barium hydroxide solution to neutralize the acid in the 20 milliliter acid sample. We now have enough information to calculate the concentration of the phosphoric acid in the solution. But before we do any calculations, we first have to generate our balanced chemical equation based on our knowledge of acid-base reactions, which we know give us a salt of some kind plus water as the two products. So let's write water in as one of the products. The trick to writing acid-base reactions and balancing them is to identify the nature and chemical formula of the salt that is produced. The salt is going to be an ionic compound formed from the metal cation of the base, in this case the barium ion, and the non-metal anion from the acid, in this case the phosphate ion. So we'll put the barium ion and phosphate ion together to give barium phosphate as the identity of the salt in this particular reaction. But we've got to ask ourselves, is this the correct chemical formula for barium phosphate? Well, barium is a group 2 metal. It will be a 2+ charge ion in its ionic form. Phosphate is a polyatomic ion with a 3- charge. Clearly, these two ions will not come together in a 1-to-1 ratio. If we do our crisscross method, we'll take the 2 from the 2 plus charge of barium and bring it down as the subscript for phosphate. And we'll take the 3 from the 3 minus charge of phosphate and bring it down as the subscript for barium, giving us Ba3PO42 as the chemical formula for barium phosphate, which we now substitute into the chemical equation above. Now that we have the correct chemical formulas for all of our substances in the overall chemical equation, the next thing we have to do is balance this equation. And in balancing the equation, we will put a stoichiometric coefficient of 2 in front of the phosphoric acid, 3 in front of the barium hydroxide, and 6 in front of water. And we now have our balanced chemical equation. 2 lots of phosphoric acid plus 3 lots of barium hydroxide produces 1 unit of barium phosphate plus 6 molecules of water. Let's now look at the information we've been given from the data recorded from our titration experiment. We know the neutralization reaction consumed 26.4 milliliters of 0.100 molar barium hydroxide. And we also know that we started with 20.0 milliliters of the phosphoric acid solution. And the whole point of the titration was to find the concentration or molarity of the acid solution. So this is now starting to look familiar to us, because we can go to this diagram here and recognize that we've been given the volume and molarity data of one substance, and we're being asked to find the concentration or molarity of another substance. And so the relevant part of this diagram is the right-hand side. We've been given the volume and molarity information about barium hydroxide, and we've been asked to find the molarity of the phosphoric acid solution. So in step 1, we use the volume and molarity data of barium hydroxide to calculate the moles of barium hydroxide. In step 2, we calculate the moles of phosphoric acid in the solution by using the ratio of the stoichiometric coefficients from the balanced chemical equation. And then in step 3, we find the molarity of the phosphoric acid solution using the volume information that's been provided. So in step 1, the moles of barium hydroxide will be calculated using one of the forms of the molarity equation, molarity times liters, which equals 0.100 moles per litre times 0.0264 litres. The 0.100 molar value represents the concentration of the standard barium hydroxide solution used in the burette, whilst the 0.0264 litres comes from converting the 26.4 millilitres into litres. When we do that calculation with our calculator, we get 2.64 by 10 to the minus 3 moles of barium hydroxide. In step 2, we need to calculate the moles of phosphoric acid from the moles of barium hydroxide we just calculated by using the ratio of the stoichiometric coefficients of the balanced equation. So the moles of phosphoric acid equals 2 on 3 times the moles of barium hydroxide, with the 2 being the stoichiometric coefficient of the substance we've been asked to find information about, divided by 3, the stoichiometric coefficient of the substance we've been given all the information about. So that's 2/3 times 2.64 times 10 to the minus 3 moles, with that number there being the value we just calculated in step 1. And when we do that calculation, we get 1.76 by 10 to the minus 3 moles of phosphoric acid. So in the final step, step 3, we calculate the molarity of the phosphoric acid solution using the molarity equation. Molarity equals moles divided by litres, which is 1.76 times 10 to the minus 3 moles divided by 0.0200 litres, with this number coming from the value we just calculated in step 2, and this value coming from the original 20.0 milliliters of phosphoric acid we had in the bottom of the titration, and which we have converted into litres. When we do that calculation, we get a concentration of phosphoric acid of 0.0880 moles per litre, or 0.0880 molar. So the concentration of the original phosphoric acid solution is 0.0880 moles per litre. And we got that answer by deliberately constructing a titration experiment where we knew the volume of the acid solution, we knew the concentration of the base solution, and we recorded the volume of the base solution consumed at the point at which the neutralization reaction was stoichiometrically equivalent.